Hi everyone, this is Ms. Shea. This is the second part of our functional groups lecture. In this video, we are going to be looking at 7 more functional groups, and at the end of this video, we'll also be looking at benzene in a little bit more detail. So let's get started. The next functional group that we are looking at is the halogen. These compounds are alkanes that have one or more of their hydrogens replaced by halogens. They're collectively known as halogenoalkanes, also known as haloalkanes or alkyl halides. The general formula of halogenoalkanes is Rx, where R is a hydrocarbon chain and the X is a halogen, meaning fluorine, chlorine, bromine, or iodine. Unlike the other compound classes that we've seen so far, these compounds are named with a prefix, fluoro, chloro, bromo, or iodo, instead of having a special suffix. Now let's look at number 25 through 28 in the guided practice packet. In number 25, we're going to draw bromoethane. Since this is an ethane, it's going to have 2 carbons bonded by a single bond. The prefix bromo tells us that there is a bromine bonded to one of the carbons, replacing one of the hydrogens. And now we need to fill in the hydrogens to complete this structural formula. The condensed structural formula would be CH3, CH2, Br. Number 26, we're going to draw 1,2-dichloroethane. Again, this is an ethane, so it will have 2 carbons bonded by a single bond. It says 1,2-dichloro at the beginning of the name, which means carbon 1 has a chlorine attached to it, and carbon 2 also has a chlorine attached to it, and we just now have to fill in the hydrogens to complete this structural formula. The condensed structural formula would be CH2Cl, CH2Cl. In number 27, we're drawing dichloromethane. Methane only has 1 carbon. Now normally it would have 4 hydrogens, but since it is dichloro, 2 of the hydrogens are replaced by 2 chlorines. The condensed structural formula would be CH2Cl2. In number 28, we are given a full structural formula, and we are supposed to name this compound. There are 3 carbons, so this is propane, and there is a bromine on carbon 2. So we would name this 2-bromopropane. Now just like with the alcohols, halogenoalkanes can be primary, secondary, or tertiary, depending on how many carbons are attached to the carbon that's attached to the halogen. So in number 25, the carbon that is attached to the halogen is bonded to one other carbon, so this is a primary halogenoalkane. And in number 28, the carbon that is attached to this bromine has 2 other carbons attached to it, and so this would be a secondary halogenoalkane. Our next functional group is the ether group, which is an oxygen atom separating 2 hydrocarbon chains. The general formula for an ether is ROR'. R is a hydrocarbon chain, and R' is another hydrocarbon chain. The name of an ether is in the format alkoxyalkane. For example, if R and R' both consist of only 1 carbon, then we would name the compound methoxymethane. If the two constituents are different hydrocarbons, then the simpler one is named first. Now let's look at number 29 through 31 in the guided practice packet. Number 29, we have ethoxyethane. Eth means two carbons, so we know that both hydrocarbon chains have two carbons. And then all we need to do is fill in the hydrogens on the carbons. The condensed formula would be CH3, CH2O, CH2, CH3. In number 30, we are supposed to draw methoxymethane. Meth means one carbon, so both carbon chains would have one carbon only. And then fill in the hydrogen atoms where they are supposed to go. And the condensed formula would be CH3O, CH3. For number 31, we're going to name this compound. We can see that the hydrocarbon chain on the left only has one carbon, and the carbon chain on the right has two carbons. Well, one carbon is simpler, so that will be named first. So this compound is going to be named methoxyethane. Our next functional group is the ester group. Now the ester group is derived from a carboxylic acid, which you may recall would have the carboxyl group, which is COOH, at the end of the carbon chain. In an ester, the H has been replaced by another carbon chain, or an alkyl substituent. So the general formula for an ester is RCOOR'. R is a hydrocarbon chain, and R' is another hydrocarbon chain. The name of an ester is in the format alkyl alkanoate. So for example, if both hydrocarbon chains consist of two carbons, then we would name the compound ethyl ethanoate. The alkyl substituent, meaning the hydrocarbon that replaces the hydrogen, is named first. Let's look at number 32 to 34 in the guided practice packet. Number 32, we are supposed to draw ethyl ethanoate. Eth means two carbons, so we'll draw two carbons, then put in the ester group, and then draw in another hydrocarbon chain with two carbons. And then fill in the hydrogen atoms. The condensed structural formula would be CH3, COO, CH2, CH3. In number 33, we're drawing ethyl propanoate. Unlike in number 32, the two hydrocarbon chains in this compound would be different. Since ethyl is named first, then that is the hydrocarbon chain that replaces the hydrogen in the carboxyl group. So I'm going to start by actually drawing the ester group. There it is. And then we know that the ethyl group replaces the hydrogen. So eth means two carbons right there. And then the other hydrocarbon chain should have three carbons. So we already have one. So 1, 2, 3. So that is the basis of this compound, and now we just fill in the hydrogens. The condensed structural formula would be CH3, CH2, COO, CH2, CH3. In number 34, we're supposed to name this compound. The two hydrocarbon chains are different, And we're supposed to name the carbon chain that replaces the H in the carboxyl group, which is this one. Since it only has one carbon, we'll name it methyl. The other carbon chain has 3 carbons, so we'll name it propanoate. So the classes of compounds that we've gone over so far are the compounds that the IB subject guide says that you need to be able to name. And that includes alkanes, alkenes, alkynes, alcohols, aldehydes, ketones, carboxylic acids, halogenoalkanes, ethers, and esters. You do not have to be able to name the compounds that contain the functional groups that we are going to talk about next. However, you need to be able to identify those functional groups. The next functional group is the amine group. The amine group is simply a nitrogen atom that is attached to one or more alkyl substituents, meaning hydrocarbon chains. Remember that a nitrogen atom has 5 valence electrons, which means it can form 3 bonds. So the amine group can have 1 to 3 alkyl substituents attached to it. And the nitrogen atom itself would have a lone pair. Just like the alcohols and the halogenoalkanes, amines can be primary, secondary, or tertiary, depending on how many alkyl substituents are attached to the nitrogen. And the name of an amine ends with the suffix amine. We'll go ahead and draw the few amines that are in your guided practice packet. However, you are not expected to be able to name or draw amines. So in number 35, we have methylamine, which is a methyl group, a carbon atom, attached to an amine, the nitrogen atom, and the nitrogen atom will have 2 hydrogen atoms bonded to it, and the carbon atom would have 3 hydrogen atoms bonded to it. So that's the full structural formula, and the condensed structural formula would be CH3NH2. In number 36, we have dimethylamine. Di means 2, so we have 2 methyl groups attached to the nitrogen of the amine group. And the third bond from the nitrogen would be attached to a hydrogen. And don't forget to fill in the rest of the hydrogens for the carbons. And that's the full structural formula for dimethylamine. The condensed structural formula would be CH2NHCH2. In number 37, we have trimethylamine. So this time we have all 3 bonds from the nitrogen going to a methyl group. And the condensed structural formula would be CH3,3N. And in number 38, we got butane-2-amine. So in this case, we have a butane, which is 4 carbons long. And on carbon 2 is where the amine group is attached. And now we just need to fill in the hydrogens. So this nitrogen should have 2 more bonds, and the rest of the carbons should all have 4 bonds. So there's the full structural formula, and the condensed structural formula is CH3, CH, NH2, CH2, CH3. The next functional group is the carboxamide group. The carboxamide group is a nitrogen atom attached to a carbonyl group. Notice that the nitrogen atom still has 3 bonds. One of them is to the carbonyl group. The other 2 would either be to hydrogens or to carbon chains. And a compound that contains a carboxamide group is classified as an amide. And here we can see an example of an amide. This is ethanamide, and the carboxamide group is right here. Our next functional group is the nitrile group, which is a carbon bonded to a nitrogen with a triple bond. The general formula is RCN. Again, R is a hydrocarbon chain. Here we have an example of a compound that has the nitrile group, and we can see that the nitrile group is right here. Our next functional group is the phenyl group. The phenyl group is the benzene ring. Compounds that contain the phenyl group are known as arenes or aromatic compounds. And the general formula of the phenyl group is C6H5. Now benzene, C6H6, is the simplest arene. We have actually talked about benzene in topic 4. What you're seeing on the screen right now is the Kekuli structure of benzene. It is a 6-sided ring with a carbon atom at each vertex. The carbon atoms are bonded by alternating double and single bonds, and each carbon atom is bonded to a hydrogen atom. However, we now know that benzene doesn't actually have alternating single and double bonds. It actually exists as a resonance hybrid structure that has delocalized electrons. This means that the electric charge of the electrons that make up the 6 bonds are actually evenly distributed, and they are not localized into single and double bonds as in the Kekuli structure. We have several pieces of evidence that tells us that benzene is actually a resonance structure and does not have the alternating single and double bonds. The first is a physical evidence. You should recall from topic 4 that single bonds are longer than double bonds. So if benzene has alternating single and double bonds, then we should be able to see that in the bond lengths. However, the 6 bonds that connect the carbon atoms all have the same bond length. So this tells us that benzene actually has a resonance structure with the electrons delocalized, evenly distributed among the 6 bonds. The next piece of evidence is a chemical evidence. This has to do with a type of reaction that alkenes undergo called hydrogenation. In hydrogenation, hydrogen is added to the alkenyl functional group in an alkene, forming an alkane. Cyclohexene is a cyclic alkene which consists of a 6-sided ring that has a double bond connecting a pair of the carbons. When cyclohexene undergoes hydrogenation, the enthalpy change of the reaction is negative 120 kilojoules per mole. If benzene has alternating single-double bonds, meaning it has 3 double bonds, then the enthalpy change of the hydrogenation of benzene would be negative 360 kilojoules per mole, basically 3 times the enthalpy change of the hydrogenation of cyclohexene. However, the enthalpy change of hydrogenation of benzene is actually negative 210 kilojoules per mole. So this tells us that benzene cannot possibly have 3 double bonds. The third piece of evidence has to do with something called the 1,2 disubstituted benzene compounds, such as the one that I am drawing right now. In a 1,2 disubstituted benzene compound, 2 of the hydrogens, specifically the hydrogen on carbon 1 and carbon 2, are substituted with something else. In this case, I have drawn a 1,2 dichlorobenzene. If benzene actually has alternating single double bonds, then there will be 2 isomers possible for this compound. However, only one isomer exists. So this tells us that benzene actually has resonance structure. And finally, the last piece of evidence is a chemical evidence. This has to do with a type of reaction called addition reactions, and we will talk about these later on in topic 10. For right now, what you need to know is alkenes easily undergo addition reactions. So if benzene actually has 3 double bonds, then it should undergo addition reactions pretty easily. However, benzene does not undergo addition reactions easily, and that tells us that benzene actually does not have 3 double bonds. So because the bonding in benzene is best described by the delocalization of electrons, it is often represented by drawing a hexagonal ring with a circle in the middle of it, instead of drawing the Kukui structure. Here we see a variety of aromatic compounds, or arenes, all of which contain the phenyl group, which is the benzene ring. And this concludes our lecture on the functional groups.